Welcome to Spring LIB.
Okay, so we're going to do chapter 29, problem 51. So we have this picture over here, and what this has is we have a current carrying wire here with the current going upwards. And next to this, there's a wire loop of dimensions A by B in a square rectangular loop, and it's positioned R away from the wire. And it says it's moving to the right in the positive x direction to the right, away from the wire at a speed v. Okay, so first it wants us to calculate the EMF induced on this wire a couple different ways. Now, usually this is pretty easy because just Faraday's law is given as the magnitude is given by the change in magnetic flux with respect to time. But this can be hard if the flux is not constant, and that's exactly the case we have here, because as some parts of the loop are farther away from the wire or closer, and the B field from the wire is dependent on the distance away. It's dependent on B of R. Okay, so let's write down what the B field of a wire is. So this comes from a previous example here. So it's mu naught times the current through the wire over 2 pi and the distance away. We're going to be in the x direction here, so we have this. So now we need to write what the differential of the flux is going to be. So this is as A is our constant, but B now changes with x. So this is dB. And this is the same thing as B times this will be times dx. Okay. So now we can write this out again and fill in what B is here. So we're left with mu naught I over B over 2 pi, and this is dx over x. Cool. So now we can finish this out to figure out what the total flux is going to be. We'll have to integrate this so we can see that the total flux is given as the integral of the derivative flux, and we can rewrite this now as what our expression for the derivative is g over 2 pi, and now we have an integral, and since our differential here is dx, so we're integrating from x, so our x starts at r because that's for the first, and it adds up a, so we're going to integrate from r to r plus a. That's our bounds, and the integral is dx over x. Cool. So we can just do that integral now, and we see that this becomes mu naught I b over 2 pi times the natural log of r plus a over r. Cool. So this is what we have for magnetic flux, but we see for Faraday's law, we need the time derivative of this. So we got to figure out what this is. And this is the same thing as the r derivative, doing the chain rule here, which is the same thing as the time derivative of the flux times the speed. Cool. So we can plug all that in, and we should see that the magnitude of our EMF should be the magnitude of the r derivative. That's r derivative. R derivative, so mu naught I b over 2 pi. Then we take the v, now take the r derivative of this natural log, and we should be left with negative a over r plus a. So we simplify this all out, and we're left with mu naught I a b v over 2 pi r times r plus a. Cool. We got there. So now we want to check this by, instead of using Faraday's law and integrating, let's do this another way. Another way we can do it is find the motional EMF from BVL for each bar in our circuit. So if this is our circuit, we can label these as 1, 2, 3, and 4. Okay. And we can easily see here that the total is just going to be the sum of all of these. So from I is from 1 to 4. But now what we can also see is since bar 2 and 4 are parallel with the speed, that's not going to contribute any EMF, because if we do the vector version, we have this given as dv dot or cross v dot dl. So if this becomes perpendicular to L, then this is going to be 0. And that's exactly the case for 2 and 4. So E2 and E4, those EMFs are 0. Okay? So that makes this a little bit easier because now we just have to find what E1 and E3 are. So E1 we can write as BVL. If we write that out, we see that this is mu naught I VB little b over 2 pi r. Okay, we can do the same thing for E3 and it'll come out exactly the same, except on bottom, instead of r, we have r plus a, because that's how far away it is. Cool. So now, the next thing is, if the force is pushing up in both of these, they're opposing each other. But we also know that the force on 1 has to be greater than 3 since the magnetic field is greater on that side. So that means the net EMF has to be 1 is bigger, so we can take the difference 1 minus 3 because we know they're opposing each other. But we know one's going to win because we already know the argument that that's going to be bigger. So if we take these subtractions and simplify it out, we're left with mu naught I ABV all over 2 pi r times r plus a, which is exactly what we had before. So this way works out just as good. Could be easier for you, could be harder, so you can choose your way, but now we've got it both ways, so let's move on to B. So we're going to get a new page here. So B asks us to figure out what is the direction of the current induced using two ways. So first way, we're going to use Lenz's law. So Lenz's law tells us that the current induced is always wanting to oppose the change in flux. So in our case here, we have a flux that is into the page and decreasing. So if that's decreasing, we want to oppose that change. So that means the induced B field is also into the page. So if we do right-hand rule, what current induced will give a B field into the page? That's clockwise. Okay, so now let's do this, figure out the same thing, but using a force argument instead of Lenz's law. So let's draw a little diagram here. Here's our wire, and here's our circuit, right? Just like before, when we said the B field is bigger at side 1 than 3, if the B field is bigger, that means the force pushing the charges upwards is greater. If this force, that means the force at 1 is greater than 3, And if they're both opposing, 1's wanting to go this way, 3 is wanting to go this way, 1 is going to win. So that means if 1 wants to push the charges upwards and around, that means F1 wants clockwise. So the current is clockwise. But that's using the force argument instead of Lenz's law. Cool. Okay, so now let's move on to C. So this tests a couple different cases. So the first case, we want to see what the how the EMF is in the following cases. And the first case is loop stationary, so that means V equals 0. Awesome. So if V equals 0, we already see that our EMF equation is 0. So that makes sense. Our equation checks out, right? Because we don't expect any induced things if that change in magnetic flux is 0. And if it's just sitting there, there's no change in magnetic flux. Cool. So now we want to do a really thin loop, which means A is 0. So A is almost 0, right? Again, we can look at our equation and see that this leads to being a flux equals 0, right? If we have an infinitely thin loop, there's no area for the flux to go through. 0 flux means 0 EMF. Okay, awesome. And now lastly, the third case. This is if we're infinitely far away, so R goes to infinity. Well, if we're infinitely far away, that means the B field is an inverse R relationship, so B of R goes to 0. No B field means no flux, which means no induced EMF. Simple as that. Can't have any of this induced EMF, no magnetic induction if there's no magnetic field. That's it.